Hi, thanks so much for having me. I'm really, really excited to be here and to share with you this story, which, in my opinion, and I understand I'm biased, having just suffered through a lot of grad school about it, but I think this is one of the most interesting stories that we as a species can tell, which is the story of our universe and the story of the birth of our universe as seen by the most sensitive cameras ever built. That we operate in some of the strangest places on Earth. I think it's an incredible privilege to get to work on these questions professionally, these like really fundamental questions about our universe and our existence. And so I'm super excited to share it with you. I identify as a cosmologist. So what does that mean? Cosmology comes from the Greek cosmos, or the order of the universe, and it's essentially attempting to study like the universe as a whole. So questions like, where did it come from? What is it made out of? Like, how much of it is the stuff that you and I are made out of, matter and atoms and stuff, and how much of it is not? How did it evolve? Like, how did we get from whatever the universe was before, if there was a before even, to this thing that supports like stars and planets and galaxies and like life that can talk about it. And so therefore, like, what is our place in the universe? I always like this cartoon. It was just, I think this is one of the most, like, the oldest questions that we as a species ask, just like where did this all come from and what is our place in it? So I'm going to give you some background so that we're hopefully all on the same page. I am trying not to assume that you remember anything from high school physics, because I certainly did not get very much out of my high school physics class. So please do feel free to stop me if I later say something that you don't feel like I gave you enough background for. So you might have heard of the electromagnetic spectrum, and so this describes the whole range of light. So visible, the stuff that you and I can see, is just this tiny sliver here. And light is a wave, and so it has peaks and it has troughs, and so the distance between two peaks or two crests, two troughs, is what we call the wavelength. And so as you can see, wavelengths can be very long. So like radio waves, the stuff that you communicate with to your car radio or something, can have wavelengths of hundreds of meters or even kilometers. And wavelengths can be really short. They can be the size of nuclei, as in the case of like gamma rays. Everything emits light of some wavelength based on its temperature. And so you might have noticed, like, when you barbecue, for example, if your grill gets super hot, it starts just glowing red or orange or even white. So the hotter something is, the shorter the wavelength of its emission. And so that's why, like, as it gets hotter, it starts getting like more orange. And so something like sun is a plasma, and it burns at several thousand degrees, and so it emits mostly in the visible. It peaks in yellow, and that's in fact why humans have evolved eyes that can see in the visible, is that's because that's where the sun has most of its emission. And so we humans also have a finite temperature. We're about 37 degrees Celsius, 98 degrees Fahrenheit. And so you might have heard, like, some people use infrared cameras to see in the dark. And so that's basically just what they see is your body heat in the infrared. So humans glow at some infrared temperature. And so if you put on some goggles with some camera in them that is sensitive to infrared light, then you can see the glow of humans. And so most of the cameras here at Lick are in the optical and infrared, so they are sensitive to light in these regions. And so just a preview of what's to come, our universe glows too, and it's at about negative 270 degrees. And we will talk about why that is and what that means in a bit. As a side note, you'll see that on these plots I use two different units, Kelvin and Celsius. This is mostly because it gets kind of annoying sometimes to keep talking about like negative large number. So 1 degree is the same in both, like 1 degree, plus 1 degree Kelvin and plus 1 degree Celsius is the same thing. But the only difference is the absolute zero. So 0 Kelvin is absolute zero of the universe. There is no temperature colder than it, and it corresponds to negative 273 degrees Celsius. And so when we talk about very cold things, it's really easy just to like compare it to absolute zero, which is why I use Kelvin. So the next piece of the puzzle is you have objects, they're emitting light based on some wavelength, based on their temperature, and they might be moving around in the universe. Stuff moves, it's allowed to do that. And if it's moving relative to us, then it looks a little different. In particular, waves moving away from us, the wavelengths get stretched out, and so objects moving away from us look red. And stuff moving towards us looks compressed, so the wavelengths get squished together a little bit, and so objects moving towards us get bluer. And so we call this Doppler shift. And you might have noticed this with something like sound waves. If you're driving around and an ambulance passes you, like when it's coming towards you, the sound waves are getting compressed, and so it's higher pitched. And then as soon as it passes you and it's moving away from you, it gets lower pitched. And so we have noticed a similar effect in light. So, putting all of this together, we want to ask the question, like, how do we study the early universe? How do we see into the past? And we can use light because light is a time machine in our universe. And this is true because light travels at a finite speed. It's very fast. It's 300,000 kilometers per second, which is like a foot per nanosecond. But it is finite. And so what that means is, take something like our moon. Our moon is 400,000 kilometers away, and that means that it takes about a second for light from the moon to get to us. And so what we're really seeing is the moon a second ago every time we look at it. And the sun, 150 million kilometers away, that takes light 8 minutes to get from the sun to us. So if the sun went out right now, I guess we would not know because it is nighttime, but people in Hawaii or something wouldn't notice, or people in Asia wouldn't notice for 8 minutes, because the light that they're receiving now from the sun is the stuff that left 8 minutes ago that is just now reaching us. And so so kilometers are getting kind of unwieldy. So we talk about distance a lot in astronomy with this term light years, the distance that light travels in 1 year. And so that's about 10 trillion kilometers. And so the center of our own galaxy, like our cosmic neighborhood, is still 25,000 light years away. It has taken that light 25,000 years to get from the Milky Way, the center of the Milky Way, to us. And Andromeda, our nearest neighbor of a galaxy, really the closest thing you can get to us astronomically, that's not our own galaxy, is still 2.5 million light years away. And so if someone were hanging out in Andromeda and pointed a telescope at us, a really sophisticated telescope that could resolve what was happening here on Earth, they would just now be getting light from start of the last major ice age here on Earth. They wouldn't see any of this right now. And so you can just keep playing this game of how you point at something in the sky and you say that's further, how far back can we see? Can we see something more than 2.5 million years away, more than 2 billion years away? I really like this etching by Camille Flammarion from almost 200 years ago now, I guess. It's trying to look past, our sun, stars, and try to figure out what, if you poke your head out, what happens past all of that. So this is the story that we're trying to tell here in cosmology. So about 100 years ago, Edwin Hubble noticed something interesting about galaxies. So first of all, he had just figured out that galaxies existed at all. Prior to the early part of the 1900s, we didn't know for sure that there was stuff in the universe that was not part of our own galaxy. But he finally figured out there is definitely stuff that is too far away to be part of the Milky Way. And in fact, it is its own galaxy. It has its own set of stars, and solar systems and everything, and it's this whole other set of galaxy, and then it turns out there are lots of them, and so he started trying to study them, and he noticed that beyond the ones that were really close to us, everything was moving away from us. So their wavelengths were redder the further that they were from us. And that's super interesting, because it implies that everything in the universe is getting bigger. And so you first might ask the question why doesn't that mean that we're the center of the universe if everything is moving away from us? But you should sort of imagine it this balloon here, right? When you blow up the balloon, there's no point that is like the center of the universe, and still everything is moving away from everything else. And so that's sort of what you can imagine with our universe, is just like everything is moving away from everything else. So everyone sees every other galaxy is moving away from them. And so Hubble concluded that therefore our universe must be expanding. And so if you just like say, well, our universe is expanding now, and we think it was probably expanding before, because why would it have stopped expanding? Then you just like keep turning that back. Then you say like, oh, then I guess maybe the universe was once really small. Separately, in the 40s, Gamow, Alpher, and Herman were trying to figure out essentially like why the chemicals in the universe had the abundances that they did. So like why there was so, in particular, like why there's so much hydrogen and helium in the universe. Because if you imagine something like our sun, so our sun is essentially this like burning ball of hydrogen, and it is so hot, it's undergoing nuclear fusion, and so it's also making helium. And if you let the star get big enough and burn long enough, then it starts forming heavier and heavier elements. So you get like, you know, carbon, and like eventually it builds like heavier elements up to iron, and then it might explode and make something like really exciting. But it turns out most of the stuff in the universe, by a huge fraction, is either helium or hydrogen. And that's very weird, because you would expect that the stars would have made much more of the heavier stuff and not so much of just hydrogen and helium, if it was just stars that was forming all of the elements. And so the conclusion that you come to then is like, maybe the universe was all like one big uber massive star at some point, so that it only made like some hydrogen and helium, but didn't have time to make anything else. Or in other words, that like once upon a time it was super small and super dense to the point that it could form hydrogen, it could fuse protons and electrons together to make a single hydrogen molecule, but that it didn't have time to do anything else. It didn't have time to make all of the heavier elements for whatever reason. And so all of these point to this conclusion that the universe once had this small, hot, dense state. And this was super controversial, because at the time the belief was, right, that the universe had always basically existed. It basically always looked the way that it does now, that like there are stars, there are galaxies, the galaxies exist sort of separate from each other. There's like these astronomical bodies, but like there is no notion that the universe 10 billion years ago, 100 billion years ago, at that like a trillion years ago should be any different than it is now. But in the 60s, Penzias and Wilson were hanging out in New Jersey. They were trying to measure radio waves bouncing off of balloons for a separate reason. And they had this source of noise that they couldn't quite explain. They tried, you know, cleaning out their electronics. They tried calibrating better. They tried pointing at like the sky and pointing at different parts of the sky and trying to make it go away. At some point, they thought that it might be pigeons that like had hung out inside this horn for whatever reason. And their notes are really sad. It says something like, took care of pigeons. But it was still there. And they realized at some point, after talking to a bunch of their friends, that accounting for redshift, what they saw matched exactly what your prediction would be for a hot, dense universe at very early times, so hot and dense that it was a plasma, so hot and dense that it was essentially like our sun, just like everything on fire everywhere, and that it, like the sun, had emitted light. At the time, it must have been about visible light, and then it just cooled off and let that light expand, redshift away from us as the universe expanded. And it cooled off enough that if you said that the universe had been expanding for 14 billion years, then that's what we would see. And so we call this, because the light that they saw, the extra noise was in the microwave wavelength, we call this the cosmic microwave background. And so this is what they would have seen. It would have been about 1 millimeter in wavelength. So it's about 3 Kelvin in temperature, extremely cold. If you imagine that plasma, as we know from our sun, is, thousands of Kelvin. And so it's been cooling off for a very, very long time. The glow in the center of this is emission from our own Milky Way galaxy, which is hotter. And so that's why it looks white to you. And this is the glow from a 3,000 Kelvin plasma that's just been extremely redshifted as it's moving away from us. And so we call this the cosmic microwave background, the CMB. It's the oldest light in the universe. Just to orient you a little bit on what you're looking at, because I realize this is just like mostly a green blob. So if you take the Earth, right? The Earth is a globe. It's a 2-dimensional object, or not a 3-dimensional object, but you can project it into 2 dimensions. And so you can flatten it, and it looks kind of weird. You do like kind of horrible things to Antarctica and the Arctic up here. But you can put the equator along the middle, and like to good approximation, you can understand that like the edges will wrap around, and this is a way of representing a 3D object in 2 dimensions. And so in the same way that you can represent the outside of our Earth's sphere in 2 dimensions, you might imagine representing the inside of some sphere that is the sky in 2 dimensions. So imagine now that you are on Earth and Earth is clear, so you can see through it and you can see in all directions. And you can just like look up at the sky, you can look down past your feet at the sky, you can look in all directions. You can make this map of like all of the stars you would see. And you can put the Milky Way in the center along the equator here. And this is again like 3D, so these edges get stitched together. And this is like what happens if you look up versus down from the galaxy that we've now stretched into 2 dimensions. And so this is like, if you imagine that the entire sky is just like some shell around you, this is the inside of that shell. And so in the same way, we can have our cosmic microwave background picture, which is the sky. And now if we just take out the galaxy, then it is really just the same color everywhere. And so we think that this is really evidence of a notion of a beginning of our universe. Like, we don't necessarily know that like the universe had some moment of non-existence and popped into existence or exploded or anything. But what we do know is that there was some hot dense state, so hot and so dense that everything was in thermal equilibrium, so that you could produce this thing that is the same color everywhere, no matter where you look, and that it didn't happen infinitely long ago, because we can still see it. And so that means that even though it's been cooling a very long time, it's been cooling 13 billion years or something, it didn't cool, more than a trillion years ago. Like, it is at a detectable temperature. And so that means that it happened a finite time ago. And so we know based on, we can essentially like take this picture and put together from this that the universe, if you just like keep squishing it and squishing it and squishing it, then it was really hot and dense. And if you squish it and squish it and squish it further, then you just get to temperatures that are really hot. And we know we can recreate here on Earth, right, in our laboratories, like the physics of really, really hot things. And so we can try it. And it turns out that taking all of the stuff that we know from our laboratory experiments of like what happens when you heat stuff up enough, like, ions start forming, and eventually like it gets so hot that like protons fall apart and they just turn into like their constituent subatomic particles. All of these things, if you just imagine that they happen in reverse, so once upon a time the universe was really hot and it was like only subatomic particles, and then it cooled off, and then like particles formed, and then it cooled off, and then atoms formed, and then it cooled off, and then like it released the light. All of that is consistent. It creates this picture that correctly explains what the CMB looks like, and it correctly explains what our modern universe looks like, and it introduces no new physics. Like, we can take the laboratory physics that we understand here and just say like, what if all of that happened everywhere in the early universe? And it turns out that works, which is incredible. Like, that we think that we have this picture for how physics works now, and that it maps onto how physics worked back then. And so like, just at this moment of where the CMB gets released, so once upon a, like, we know that if you just like take matter and you just like squish it really, really hard, eventually it gets so hot and so dense that electrons are like, we don't want to hang out with you anymore, hydrogen and helium, like we would rather just be our own free agents. And so all of these particles ionize. And light really likes to interact with charged particles. It doesn't really like to interact with hydrogen, neutral hydrogen and helium, but with charged particles like free electrons, really loves to interact, really loves to bounce and get reabsorbed and scatter and get re-emitted. And so this entire section is opaque, like you can't actually see through it. So it's kind of like, it really is just like our sun, right? Like our sun is so hot that it's ionized, and that's why like we can't see through it. So light, I think the thing that I was taught in school is like it takes about 1 million years for light to travel from the inside of the sun to the outside of the sun, where it finally gets just streamed towards us, because it takes so long just like bouncing around all of the different charged particles. And in the same way, like light is just hanging out, bouncing around, and at some point the universe just cools off enough that the electrons are like, oh, wait, we want friends, it's cold, you know, safety in numbers. And so they find like a buddy, and they become neutral helium, neutral hydrogen, and the light doesn't have any charged particles to bounce off of anymore. And so it just starts free streaming. And it turns out that our universe is pretty empty. And so for the most part, this light that just bounced off of this last set of electrons, free electrons, in the early universe has just been traveling towards us until it lands on our detectors. So 14 billion years. And so we try to understand our early universe essentially by trying to measure this light, because this light comes from the surface of last scattering. It is the last set of things that we can see. Past this, it is just an entire wall of this opaque fog. Like you can't see past it. It's just like fog everywhere. And that's it. That is as far back as light from our universe travels. And so we want to try to understand like what happened before all of this, which we cannot see because we are blocked by, you know, this entire fog. And so what we do is we just like measure this light incredibly well and try to use it to understand stuff about our universe. So for example, we can study the spectrum of the light. So basically like how much of it comes in different colors. And from this, we get that this is what we call a perfect black body spectrum. And so this is the temperature, this is the prediction for what would happen if everything was exactly the same temperature. And so this is in fact the best measured black body in the universe. The error bars are 400 sigma, and so for people who remember anything from their statistics classes, like 3 sigma is 99% confidence, 99.7% confidence interval, something like that. 5 sigma is usually the gold standard for you definitely detected something interesting about the universe. 400 I don't know that I'm not a simulation at 400 sigma, so I don't totally know what they mean by this, but it's like this is an incredibly precise measurement in which we understand that the universe really was just like entirely the same temperature at some point everywhere. And from all of this, you can make a prediction for how much of the various elements you get. So like how much hydrogen and helium and lithium. And if you just like go out and measure the abundances of chemicals in the universe, you find that there's an exact match. So this is from measuring this full sky picture. And so, like we said, it's really the same temperature, like it really is the same temperature everywhere. But if you look really, really closely, like you add a bunch of digits to your thermometer, you actually find that if you stretch the color scale enough, you do get small patterns in the temperature. And if you build a higher resolution instrument, then you can get even nicer pictures of like the bumps and wiggles in this temperature. And so these temperature deviations are, we say, 1 part in 10 to the 5. So you need like 5 decimal places on your thermometer before you can see something like this. And this is essentially how we build our modern picture of the universe, because what we're seeing here then is small differences in that surface of last scattering, that last set of electrons. And from this we can infer, like, given that it made this pattern of hot and cold spots, what must it have been doing such that this part of the universe ended up like a tiny fraction of a degree hotter or colder than this other part of the universe? Why does it make patterns of this particular size? Why does it make patterns with like this particular size, both in like how big the temperature fluctuation is and also like how big of a scale this is? Like, why is it this far across and not this far across or huger, right? And so from all of these things, we can figure out all sorts of things about the universe. So it turns out that like just from looking at something like this picture and then asking questions about like what physics must have been happening such that you get this pattern, not any other pattern, we have figured out the shape of the universe. We have figured out how much matter there is versus something like dark matter. So you might have heard of dark matter as this mysterious thing that is heavy, like it interacts with gravity, and doesn't interact with light. And so we don't know anything else about it except that we just know it's heavy and it's out there. But we know just from this this set of patterns, like how much of it there must be out there. We can figure out something like when the first stars turned on. We can figure out the age of the universe just from looking at this picture. And so from that, like, what have we figured out? So we're gonna take this picture. This is the most recent one we have of the full sky. It's from the Planck satellite, which is the European Space Agency. And from this, just like looking at the size of the various patterns, we essentially have our timeline for the universe. So time is going to start at the very left, and we're going to go across the screen. And the black curve is essentially like the size of the observable universe. And so we don't really know what happens in the beginning. Could be anything. Doesn't necessarily have to even have been a beginning. It might have just been very, very small, infinitely long ago. But we know that at some point it went from small to not small anymore, and approximately our size. And we know that less than 10 to the minus 11 seconds into our modern universe, as we understand it, so a millionth of a second, we know that all of the particles that we understand must have formed by then. So anything that they have ever found at like the Large Hadron Collider in Geneva, we know must have existed by this point. We know that by 1 millisecond in, the first protons were beginning to form, and the first protons cooled down as the universe expanded, hung out, interacted with each other, all those sorts of laboratory physics that we can actually just build lab experiments to test. Now we know that that hydrogen and helium plasma with the light bouncing around the electrons was happening as the universe is expanding and cooling. And then about 380,000 years into this process, we know that the CMB was emitted. So the light recombined with the electrons recombined with the ions, and the CMB got released. And then it was actually really boring for a while. So there's neutral hydrogen and helium now, and there's really nothing else in the universe happening because now we just have a bunch of neutral atoms. And so we call this the Dark Ages. And the only thing that's happening is gravity, really, is just making things clump together slowly over time. And eventually some stuff gets close enough and dense enough that it starts collapsing again and it starts burning into the first stars. So it gets dense and hot enough in small patches that you start supporting something like nuclear fusion, and so you get the first stars about 100 million years in. And And then about 1 billion years in, those stars start forming into bigger structures, so the first galaxies. And that process has essentially just been continuing ever since, of just like stuff collapsing under the force of gravity to our present day, which we understand to be about 13.8 billion years into this picture. And so this is just from measuring the CMB, essentially, that we have formed this picture, which I think is incredible. You might have also heard like JWST, this new NASA satellite got launched Christmas Day last year, and they keep talking about like how they're making some of the oldest pictures of the universe. They're mostly measuring like the oldest objects, so they are mostly measuring in this range here, like between the first stars and first galaxies or so. So, 12 billion years ago, 12 or 13 billion years ago, very impressive, but not nearly 13.8 billion years ago. Other questions, so we have other questions about the universe then, right? And so we would like to understand them. We would like to understand what dark matter is. I have essentially glossed over the fact that there is this thing called dark energy that exists, we think, and what we know about it is that it is making our universe, the rate of expansion of our universe, like how fast everything's moving away from each other, that's actually getting faster. So stuff is not only like moving away from each other, but it's moving away from each other like faster and faster and faster. And we don't really know why. And so because we're very creative, when we don't know how something works, we're just like, call it dark, it's fine. And so that's dark energy. We know, the basic story of like approximately when the first stars turned on 100 million years in, but we don't actually know like what the mechanics were behind that. And so we'd like to better understand, like, did they all turn on at once? Was it some chain reaction effect where once one started, it started all the other ones in their neighborhood? Or were they pretty isolated from each other? Not totally sure. We'd like to understand stuff like that. We'd like to understand the distribution of matter in the universe. So, we know that everything came from that picture, right? It is the initial conditions problem from which, like, our modern universe must have been derived. And so given that we have this point A and this point B, like, you should be able to come up with physics that connects, like, what was happening 14 billion years ago to what is happening now. And so that means that you should be able to just connect like where all of the mass is based on the early picture. And also, if you can connect point A and point B, then you should be able to wind that clock backwards even further. Like, if you can say the CMB looked the way it did 14 billion years ago, and our universe looks the way it does now at present day, then using that same physics, can you go further back past the CMB? Can you figure out what happened before those first particles formed? Can you figure out what happened at the very beginning? And so in order to make all of these measurements, essentially what we want to do is we want to make like even better maps of the CMB. We want to measure it, those temperature differences, to many, many more decimal points. We want to do it at, all sorts of different scales. Like, we want to make maps of the big features. We want to make maps of the small features really, really precisely. And so how do we build tools to precisely map the CMB? I'm going to use a very, I think, naive analogy, but essentially the way that we do this is we collect the light and we measure the temperature. So you get the light from the CMB. It's been traveling a very long time, and it lands here on our detectors. And our detectors are essentially just giant buckets that we have designed to collect CMB light and try not to collect any other light. And then we just stick a thermometer in it and ask, what temperature is it? And so the thermometers that we use are these really exquisitely sensitive, what we call transition edge sensors, and they are these superconducting detectors. So they rely on the sharpness of the superconducting transition to essentially measure the temperature of the light incredibly precisely. And the great advantage of these is that you can lithograph them. So using the same techniques that you use to like lithograph all the transistors and circuits and whatever that, you know, Silicon Valley got its name from, you can just print all of these pixels onto silicon wafers exactly the same way, same processes. And in this way, you can make cameras that consist of like hundreds or even thousands of sensors. And so, you know, 20 years ago, when I saw a bucket of light, it really did kind of look like a tiny little bucket. And it was really hard to do this because of these modern lithography techniques. We can go from like 50 sensors in a camera. 10 years ago, it was like 2,500 sensors in a camera. So this picture was taken at SLAC, National Accelerator Laboratory in Menlo Park. And one of the cameras that I worked on for my PhD, they're like, in fact, trying to install right now in down south, and it is about 50,000 sensors. Like, we are just increasing by orders and orders of magnitude because it has become so easy to just print like these arrays of sensors. Otherwise, these cameras are actually not so different from the ones that you're familiar with. So we have lenses and filters, just like, you know, your regular SLR setup or like the ones here at Lick, but they are a different wavelength. So instead of optical elements, these are now like microwave wavelength filters. And so because the wavelengths are longer, everything is just bigger. And so this is a human. My friend James, who is normal sized for scale, he is not extremely large or extremely small as humans go. And so it turns out to be way easier to make a lot of these like filters and lenses and whatever, because your wavelengths are much bigger, and so you can get away with like messing up a little bit more in your machining. But unfortunately, it also means like can't walk into you know, B&R camera or wherever, or go on eBay and like just type in microwave lens and have them ship something to you. So we do have to build all of these ourselves. So it's a lot of arts and crafts. One of the other things that I think is kind of fun is, so we are trying to measure this 3 Kelvin object, right? And so you don't want your detector to be hotter than the thing that you're trying to measure. And so you need to cool down your detector to below 3 Kelvin. And so we use essentially a really fancy refrigerator. So normal refrigerators, like the kind you have in your home, probably the refrigerator part is like 270-ish Kelvin, the freezer part 250. But we use all sorts of technology, mostly pulse tube cryocoolers now, which is essentially a really fancy version of like a regular refrigerator, or but sometimes people use liquid helium, which boils at 4 Kelvin. And then from there, we use all sorts of special tricks with helium-3, which is a rare isotope of helium. And it has a lower boiling point to get us to something like 250 millikelvin or something like 10 millikelvin, so 0.01 degrees above absolute zero. And we need this to cool down our detectors enough that they can see differences in the sky and not like just thermal emission from looking at themselves. And so there's a lot of fun tricks in just trying to get stuff really cold, because it turns out us humans and everything, like all of our computers, hang out at room temperature, and you want to interact with something that is, you know, 0.25 degrees or 0.01 degrees or something above absolute zero. And so the exercise of just like trying to communicate with an electronics object that cold is a lot of what we do. And so let's say that you've actually done it though. You've like built this camera, it's very cold, you've got lenses and filters, you've got your like wafers of silicon filled with your detectors. Where do you put it? Ideally you'd go to space, but space is very expensive. NASA doesn't let you just like call and say, hey, like throw this in space for me when you get a chance. And so from Earth, you want to go to a place where it's very high and dry. So it's totally fine for us to observe during the day, because we're observing in the microwave, and so it doesn't matter that like the sun's visible light is coming down on us or not. But we do want to avoid water and atmosphere, because atmosphere just gets in the way, and water, and is also made of water, and water absorbs microwaves. So this is the same reason like your microwave heats up your food, is because there's water in your food, you stick it in the microwave oven, it zaps microwaves at it, the water heats up because it absorbs the microwaves, and then your food heats up. And this means that any water in front of our telescope absorbs the microwave signal, and then we can't see it. So the best places on Earth to do this are essentially all of these very dry places. So this is essentially a map of like how much water there is in the atmosphere. And so here in the Bay Area, we're like doing decently well, but there are definitely drier places. There's a strip down in Chile where a lot of telescopes are. And so you might have heard of like Vera Rubin Observatory or ALMA or the Simons Observatory. So these are all telescopes that for one reason or another hang out in Chile, where it's an elevation of like 5,000 meters and very dry. But one of the best observing sites on Earth is Antarctica. And in particular, the telescopes that I worked on in my PhD were mostly based at the South Pole. And so the South Pole is extremely dry. I looked it up a few hours ago. It was about a factor of 50 times drier than it is here on Mount Hamilton. It is high altitude. It is about an elevation of 10,000 feet at the South Pole, because essentially the entire Antarctic plateau, most of the continent except for the stuff on the coast, is just like up on this glacier. So elevation of about 10,000 feet. And a nice thing is that there's one night that's 6 months long. This is not so much because like we can't observe during the day, but because the sun, when it rises and sets, it causes turbulence in the atmosphere because it's like heating up the entire atmosphere. And so because most places it rises and sets once a day, like it mixes up the clouds and stuff and all the water as it heats up, and so that makes the clouds move around in really annoying ways. And so it's really nice that the sun rises and sets very slowly at the South Pole, because it means that it's very stable observing conditions. It also happens to be the case that the U.S. Antarctic program is excellent logistical support, so they provide power, they provide planes, they feed us, they run a very excellent trivia night, and so there's a long legacy of CMB telescopes based at the South Pole for the last several decades. One cool thing for amateur astronomers in the room, so you might have tried to take like star trail photos of stars moving across the sky at night. Because we're at the South Pole, the sky just spins in a circle overhead. So that means that your star trails form a perfect ring. And for us, that's awesome because it means that any part of the sky that we're trying to observe to take a map is always at the same elevation. And so you just like point your telescope and you can just like make it go in a circle, and it will just follow the same part of the sky, and it will never go below the horizon, it will never go up. And so you can just like set your telescope and just like let it track, which is awesome. So how do you get to Antarctica? You first fly to New Zealand. For the U.S. Antarctic program, the base is in New Zealand. New Zealand is a beautiful country. Highly recommend it. There are a lot of sheep. That's this picture. No, I like woke up on my flight my first time there, and I looked out the window, and it was just all these sheep, and I was like, it's like they told me. Yeah. And then you take these ex-military planes, so this is a C-17, it's a cargo plane that they use, and to the coast. This is McMurdo Station, and it's the base for U.S. Antarctic program operations, and so it supports a crew of about 1,000 people, and so that's like contractor staff, like people who cook the meals, the electricians, the carpenters, the plumbers, and like the pilots and everything, all the cargo people, and also all the researchers. So there are people like me, so that study cosmology, but they're also like biologists who study the marine, the wildlife. This is Mount Erebus. It's the southernmost active volcano in the world. So they're like people who study volcanoes who just go out there every day and listen to what it's doing. They're like glaciologists, etc. So it's like really fun to wander around, just talk to people and ask them like what they study. From there, you catch another plane to South Pole itself. This is a specially modified C-130 ex-military plane, so this one has skis on it so that it can land on the snow, which I think is cool, and then you end up at the South Pole. And so in the summer, it's when we go because it's warm enough that the plane doesn't freeze. It's not so bad. It's like -30 to -10 degrees Celsius, so that gets up to like 10 degrees Fahrenheit. But as I said, it's incredibly dry, so it actually doesn't feel as cold as you might expect if you're used to those sorts of temperatures here in North America. So there are colleagues who come from like Wisconsin or something who are like, oh yeah, it's like way better in Antarctica than it is in Wisconsin. So the station looks like this. You have South Pole Station, you have like the geographic South Pole that everyone takes their pictures at. The skiway, this is where the planes land. And then just like, it's about a kilometer walk every day, so 15-ish minutes walk. You have your telescopes out here in what we call the dark sector. And so just a quick tour of some stuff around the station. This is what the elevated station looks like. It's quite shiny. It was built in 2008, and it's well maintained because it turns out that there's no dirt there, so it doesn't get dirty. And everyone gets a cute little dorm room. We have a science lab in there in case no one feels like walking out to the telescope for whatever reason that day. And the U.S. Antarctic Program really does an excellent job of making life pretty good for us. So there is a greenhouse, so we do get fresh vegetables. Otherwise, in the summer, the planes land frequently enough that like you can get some bananas that have only been frozen once in their lives. And they have like an entire bouldering wall and like some cool recreation activities. The internet only comes up for a few hours every day because you need to wait for a satellite to pass over the pole, and not many of them do. And so this is a picture of us. What we did was we would like wait for the satellite to come up and download the New York Times crossword every day and print it out and do the crossword on pen and paper. And then it's like if you get stuck, you're just, that's it. That's, you don't know until the next day. But for the people who stay during the winter, like I said, it's too cold for planes to fly in and out, so we have these people called winterovers who babysit the telescope for the entire winter. And so the last plane leaves in February and the next plane comes in October. And other than that, they will watch the sunset, they will hang out for a 6-month night, they will watch the sunrise, and then like people will come back and rescue them, hopefully. And so there are about 40 winterovers per year, and they hang out with only each other for those several months. And so I'm going to show you a few really awesome photos that they get to see, which is of the auroras, which you can't see during the day when the sun is up. But I think it's incredible. Like, the whole being stuck at the South Pole for 9 months, I'm not sure is awesome, but like these are some of the pictures that they managed to capture. So this is sunset. For astronomy nerds, it's kind of fun to think about like how everything gets flipped in the southern hemisphere. So this is Mars on the bottom and the moon on top, and then the Milky Way. But even during the summer, sometimes you get to catch really cool things. So one of my coworkers last year when she was there, she's the small one there, took this photo when an eclipse was happening that passed over, that was visible from Antarctica. And so this is a time lapse of the moon, moving in front of the sun, which I think is incredible. But yeah, that's really all I had. I think the CMB is incredible. It gives us a glimpse of the super early universe, like 380,000 years into our modern universe. And it has essentially allowed us to build a picture of like how the universe came to look the way it does. Like that we can connect our understanding of lab physics all the way back like billions and billions of years to some notion of this early universe that happened a finite time ago. also that there's still more stuff to be learned. Like, I just spent a long time in grad school building tools and analyzing data, like trying to build next generation telescopes so that we can make these better measurements, so that we can try to understand more questions that we have about our universe, our place in the universe. So I think there's really exciting work to come. And so, hopefully you'll hear some cool results coming out of the CMB in the coming. Yeah. Yeah. So at this point, like, we understand our picture well enough that we essentially can say, if, for example, dark matter looked this way, then it should create features that look like that. And then so you can go and you can look at your map and say, like, does it have those features or not? The other thing that we can do, this is actually quite recent in the last couple of years, is we can say, because the CMB is this baby picture of the universe, you should be able to look at that and say, like, this is how gravity should interact with that picture. Therefore, there should be galaxies or galaxy clusters in these parts of the sky. And then you can just point a modern optical telescope in those places and look. And the correlation is really excellent. And so this tells us we can essentially take the CMB and use it to predict where stuff is in the universe through the entire 14 billion years of cosmic evolution. Yeah.
So I have a question about the Kelvin measurement. Mm-hmm. So how do we know that absolute zero is actually absolute? What would happen to what is impossible? But how what else is below that?
Right. So this is a great question. So essentially, it comes down to what does temperature mean? And temperature is, in some sense, a characterization of how much disorder there is or how much randomness there is in the system. And so stuff gets more and more temperature as objects bounce around and wiggle around, or and so there's randomness in where their position could be. And essentially 0 Kelvin is when there is no randomness in the system. And so there is no sense in which you can go below that. Yeah. So it's just it's basically that is the definition of absolute zero, is when it is not possible for it to be more ordered.
So is it a pattern? Everything's still?
Yeah, essentially. Yeah.
So correct me if I'm wrong, but I have this intuition that in order for stars to start to form, for matter to start to come together, matter cannot be completely uniformly distributed.
Yes.
In space.
Yes.
So how did it come to be non-uniform?
That is an excellent question. The short answer is we are not totally sure, but one of the things that we are trying to do with the CMB, and in fact, one of the main experiments I worked on in grad school, was essentially trying to make measurements, trying to understand where the initial conditions came from. Oh goodness, sorry. Yeah, so essentially trying to figure out what happened here. So there is a very popular theory out there called inflation. And essentially what it says is that the universe was once really small, teeny, teeny, tiny, and it had just quantum fluctuations in it. There's some amount of randomness in the universe that just happens because, essentially Heisenberg's uncertainty principle. You don't know for sure that something is of some energy or some position. And for some reason, it blew up exponentially. And it's just those quantum fluctuations that got blown up exponentially through the process of inflation that sets why some parts of the universe are just slightly hotter and slightly colder, or slightly more dense and slightly less dense. It's just quantum fluctuations that got blown up. Otherwise, that is our best guess. Otherwise, we actually have no idea why some parts would be slightly more, slightly less dense than others. Yeah.
So when you take image signatures of the CMB, you had one from many years ago and you had a recent one. Mm-hmm. Are you noticing changes in the map, or is it just getting more high resolution as you measure it?
So there is That's a great question. There are a few ways in which the maps are getting better. We are mostly not noticing changes, though.
Over time.
Right.
Small.
Right. Like, relative to 14 billion years, like 50 years of humans measuring it does not make any meaningful difference. Although some people in the last like 2 or 3 years have started trying to use maps of the CMB to identify like very slowly changing astronomical things, because they're like, anything that changes in a CMB map can't be the CMB, but they try to use it to discover like new like galaxy clusters or like astronomical things. But yeah, so the main ways in which we are trying to make these maps better to extend the like scale of the thermometer and to make exactly like higher resolution. So it is possible to extend the scale of the thermometer but not like see finer features, because every point you just like have measured to greater precision, even if it's still fuzzy to you, if that makes sense. So those are the two directions. Yeah. Oh, sorry.
It sounds, I don't know how much they love it, but it sounds as if you're trying to measure a very narrow band of light that you assume when you model that it comes from the start of the universe. Since we seem to be able to create temperatures that are very low, and so essentially generate light at those close frequencies, is it possible you also get noise from other places that's not light?
Yes, for sure. So that's another reason that we like going to Antarctica, is because there's less stuff that's happening generally. But yeah, anything in the universe that emits microwaves looks to us like signal. So in particular, one of the things that we worry about is like dust from our own galaxy. Is very bright, and so it mostly peaks in other wavelengths, but it's so bright and there's so much of it and it's so close that like some of it does leak into the CMB. And so mostly what we do is we know that dust has a different color, and so that means that it has a different amount that you would see depending on what frequency you observe at. And so what we do is we take a bunch of measurements at different colors. So like the red map and the green map and the blue map or whatever. And we say we know that the CMB is green, for example. And so if you measure something that is blue, then you know it can't be a CMB, and so you subtract it out. Yeah.
Really specific, but how long is the exposure for a CMB image? How long?
Yeah, that's a great question. So, essentially, let's see, I actually have a backup slide on this. So this is an excellent question. So you could imagine doing the thing that you said, so taking an exposure. It turns out that this is very hard because of the atmosphere problem that I mentioned, just the atmosphere is in the way and clouds move around. And so what you would want to do if you wanted to make this exposure, right, is you would stare for some amount of time, hope that all of the atmospheric effects average away, and then just step to another place and stare for another amount of time and hope it averages away. And you don't have any guarantee that the atmosphere will average away over a 10-minute or 30-minute or hour-long time scale. And so what we do instead is we make our pixels small so that they don't overlap with each other. And what we do is we just scan them around. And so they are just continuously recording the temperature as they're moving. And what we do is we just, later in post-processing, we say we know that we record the temperature and where the telescope was pointing at every point in time, and use that to construct when the telescope was pointing in this direction, it had this temperature. When it was pointing slightly further as it scanned, it had this temperature. And when you do that, then as long as you move fast enough that clouds are not moving on those timescales, the atmosphere looks essentially frozen to you. If you move faster than the cloud moves, then it looks like the cloud is not moving. A better way to put this is for example, if you're driving and someone is walking, if you're driving fast enough, like it doesn't matter how fast they're moving, like they look still to you, and so you just need to move faster than they are by a lot. And so that's what we do. We just like move faster than we think clouds move, and so it looks still to you. And then you just take, like you scan back and forth, and you take these, you take that data, and then you just average it down that way, and that's how you get over clouds. And so we scan continuously, and so, years, I guess. Yeah.
So like, you said like the waves like cool and then the plasma capture on it. So do you have any idea how like hot or cold the universe was like when it started and like started traveling?
When the light was released at this surface of last scattering, it was the same temperature that light is released every time a plasma cools enough. This is like one of the cool things, is that like our laboratory physics is connected to this, and so we know that it was, about 3,000 Kelvin. Yeah.
Here's the vein of space telescopes.
Yes. Yeah, so besides like CMB specific telescopes, which NASA has flown a few, one of the big things that they can do is they can help make really, really good measurements of the modern universe. So all of these telescopes are essentially taking pictures of like stuff that to us is in the way. And this is useful in two ways. First is just, it allows us to subtract it out. If they tell us, there's stuff in these places that's not real CMB, we can take it out. And the second is that it gives us a very good picture of like what point B is. And so we can say, we measure the CMB really well here. We have this really good, excellent measurement from this satellite of like what point B is. We should be able to connect these. And so getting more information on both sides of that, therefore, is helpful.